Have you ever watched a flag whip in the wind? You know, seeing it ripple and snap, reacting to something you can't even see.
Or maybe notice the way cream swirls into your coffee. Those complex, sort of fleeting patterns.
Exactly. Those everyday things. They're really glimpses into this hidden world. The, well, the incredibly intricate science of how fluids actually move and deform.
It's a fascinating world, too. One where things can be moving in circles but not really spinning, if that makes sense.
And where study doesn't always mean not accelerating, which sounds completely wrong at first.
Right. So today we're taking a deep dive into something called fluid kinematics.
Okay, so what is that exactly? Kinematics.
It's basically the study of fluid motion without getting bogged down by the forces that actually cause the motion. We're not worried about pressure or friction yet.
So it's like peeling back the layers to just understand the how of the flow itself, how it moves, how it twists, how it stretches.
Precisely. We'll look at how engineers and scientists describe movement, how they visualize it, which is super important, and some surprising ways fluids can behave.
And this deep dive, like always, is designed to give you that shortcut to being well-informed. We're aiming for those aha moments that make tricky topics click.
Our mission really is to pull out the most important nuggets of knowledge from our sources today. It's a foundational text on fluid mechanics and give you a clear, hopefully engaging, maybe even fun understanding of this field.
All right, let's jump in. So describing fluid motion. If you want to describe, say, water flowing in a river, what's the first way you might think of doing it?
Well, fundamentally, there are two main ways to think about it. The first one is what we call the Lagrangian description.
Lagrangian.
Yeah. This is like trying to follow a single individual fluid particle. Imagine putting a tiny tag on one water molecule, or maybe a little speck of dye, and just tracking its specific journey.
So you're watching one specific thing as it moves through space and time, keeping tabs on its position, its velocity, moment by moment.
Exactly. Like tracking a specific billiard ball on a pool table, you know its whole story. It's kind of like a closed system analysis in thermodynamics where you follow a fixed amount of mass.
Okay, I can picture that. But for fluids, that sounds incredibly hard. I mean, water molecules are tiny, they bump into each other constantly, the flow gets messy.
You've hit the nail on the head. It is incredibly difficult. Fluid particles aren't easy to identify. They deform, change shape, and there are just billions and billions of them interacting.
So is it actually used? Or is it just a theoretical idea?
Oh, it's definitely used, despite the difficulty. It's really valuable for certain things, like tracking how pollution spreads, following the contaminant particles, or in very specific flow visualization experiments where you can track individual markers.
Right, but not for, like, designing a whole airplane wing.
Generally not for something that complex, no. For most engineering problems, following every single particle is just too much.
So if that's so hard, what's the alternative? How do engineers usually handle it?
The more common approach, the one you'll see most often in fluid mechanics, is the Eulerian description.
Eulerian. Got it.
Instead of chasing individual particles, you define a fixed region in space. Think of it like drawing an imaginary box in the river. We call this a control volume or sometimes a flow domain.
Okay, a fixed box in the flow. Then what?
Then you define what we call field variables within that box. These are things like velocity, pressure, temperature measured as functions of position within the box, and also of time.
Okay, so it's like anchoring a sensor, maybe a little propeller, at a fixed spot in the river.
Perfect analogy.
It just measures the speed or pressure of whatever water happens to flow past that specific location at that specific time. You don't care where that water came from or where it's going next.
Exactly right. You're focused on what's happening at your measurement points within your defined volume. It's much more practical for experiments like putting probes in a wind tunnel, and for a lot of calculations too.
Okay, that makes sense. It seems much more manageable.
Yeah.
But this brings us back to that tricky question from the beginning. If you're using this Eulerian view, looking at fixed points, and the flow is steady, meaning the velocity at your sensor isn't changing over time, how can a fluid particle still be accelerating? It feels like a contradiction.
It does, doesn't it? But this is where things get really interesting and fundamental. Even in a flow that looks steady from our fixed Eulerian viewpoint, an individual fluid particle absolutely can be accelerating.
How?
This is captured by a concept called the material derivative. It's sometimes called the total derivative or particle derivative. It's a special kind of derivative.
Okay, material derivative. What does it do?
It's designed specifically to tell you how a property changes if you were following a fluid particle. It sort of bridges the Lagrangian and Eulerian views for calculating change.
And it explains the acceleration in steady flow.
Yes. It has two parts. The first part is called local acceleration. This part is only non-zero if the flow itself is unsteady, like if you're opening or closing a valve, changing the flow rate over time at a fixed point.
Okay, that makes sense. Unsteady flow, local acceleration.
But the second part is the key here. It's called advective acceleration, or sometimes convective acceleration. This part accounts for the fact that the fluid particle is moving to a new location in the flow field, where the velocity might be different, even if the velocity at each location isn't changing over time.
Wait, okay. My head's spinning slightly. Can you give an example?
Absolutely. Think about water flowing through a regular garden hose nozzle.
Okay.
From your perspective, just watching the nozzle, if the tap is fully open, the flow looks steady, right? Water comes out continuously. That's the Eulerian view.
Right, steady flow.
But now, imagine you're a tiny water particle. You enter the wide part of the hose near the nozzle connection. Then you get squeezed through the narrow opening.
You speed up a lot.
Exactly. You are clearly accelerating, even though the flow pattern itself looks steady to an outside observer. That acceleration, that's entirely due to the advective acceleration term in the material derivative. You moved from a low-speed region to a high-speed region.
That's a fantastic example. Makes it much clearer. The particle's experience is different from the fixed point measurement.
And it's not trivial acceleration either. Calculations for a typical nozzle show particles can accelerate at like 160 feet per second square. That's almost 5 Gs, 5 times the acceleration of gravity.
Wow. All just from moving through a narrowing passage in steady flow.
All advective. And this material derivative idea isn't just for velocity. It applies to any fluid property, how pressure changes along a particle path, how temperature changes, and so on. It's fundamental.
That's a really powerful insight. It totally reframes how you think about steady flow. Okay, so we have these two ways of describing motion and this material derivative bridging them. But how do we actually see this stuff, especially the complex patterns?
Yeah, visualization is absolutely key in fluid mechanics. Like they say, a picture is worth 1,000 words, maybe more here. We use lots of techniques, both in real experiments and in computer simulations, CFD, computational fluid dynamics.
So what are some of the main ways we draw these pictures of flow?
One of the most basic is the streamline. Imagine drawing lines through the fluid at a specific instant in time, such that the line is everywhere tangent to the velocity vector at that instant.
So it shows the direction the fluid is moving right at that moment.
Exactly. If you drew little velocity arrows along a streamline, they'd point perfectly along the curve. It gives you an instantaneous snapshot of the flow direction field.
And I've heard of stream tubes.
Right. A stream tube is just a bundle of streamlines forming an imaginary tube in the flow. The cool thing is, by definition, fluid can't cross a streamline. So whatever fluid starts inside a stream tube stays inside that stream tube.
Ah, that sounds useful for analysis, like tracking a specific portion of the flow.
Very useful. For instance, if the flow is incompressible, meaning its density doesn't change, and the stream tube narrows, the fluid inside must speed up to conserve mass. You can see the relationship between area and speed.
Okay, streamlines are instantaneous directions. What about tracing the actual journey of a particle over time?
That's what we call a path line. This is the actual trajectory, the real path, traced out by a single fluid particle over a period. This is a truly Lagrangian concept. You're literally following one specific bit of fluid.
Give me an example of seeing path lines.
Think about waves on water. If you put some small visible tracer particles in the water and take a time exposure photograph as waves pass, you'll often see little elliptical paths.
Elliptical, so they go around in circles.
Sort of up and down and forward and back. But importantly, after one wave period, the particle often ends up very close to where it started. There's not much net forward motion of the water itself, just the wave energy propagating through it.
That's interesting. So the water mostly bobs, but the wave travels.
Pretty much, yeah. And modern techniques like PIV particle image velocimetry actually use tiny segments of path lines from thousands of small tracer particles to measure the velocity field across a whole area very accurately.
Okay, streamlines, path lines. What's the third common one? I feel like I see this one in videos a lot.
You're probably thinking of streak lines. These are the most common ones you see in physical experiments, especially with smoke in wind tunnels or dye in water.
Right, like smoke flowing over a model car.
Exactly. A streak line is formed by continuously releasing a tracer, like smoke or dye, from a fixed point. The line you see is the locus, or the collection, of all fluid particles that have passed through that specific injection point over time.
Okay, so streamline is instantaneous direction, pathline is one particle's history, streak line is all particles that pass through one point. They sound related. Are they often the same?
Ah, now that is a crucial distinction, and it's a real aha moment when it clicks.
Okay, lay it on me.
In steady flow, where nothing is changing over time at any point, streamlines, pathlines, and streak lines are all identical. They trace out the same lines in space.
Okay, that makes sense. If the flow isn't changing, the direction lines, the particle paths, and the dye lines should all match up.
And this is the important part, in unsteady flow, they are generally different, sometimes very different.
Different how?
Imagine something like an oscillating inlet, maybe air being sucked into a duct periodically. The streamlines at any given instant might still look like smooth curves going into the duct.
Okay, the instantaneous snapshot looks normal.
But if you inject dye continuously, a streak line, or track a single particle over time, a path line, those lines will be wavy or wiggle, reflecting the history of the unsteady flow. The streamlines don't have that memory. They only show the right now.
I see. So streak lines and path lines contain history, streamlines don't.
Exactly. And this can sometimes make visualizations a bit misleading if you're not careful. Think about that classic pattern of vortices shedding behind a cylinder, the Kármán vortex streak, makes flags flap.
Yeah, the swirling eddies.
If you inject smoke right behind the cylinder, the streak lines show these beautiful, strong, alternating vortices. Looks dramatic.
It does.
But if you inject the smoke much further downstream, say 150 cylinder diameters away, the streak lines often look almost perfectly straight.
What? But the vortices.
The vortices have actually diffused and dissipated much earlier. The strong pattern you saw near the cylinder was, in a way, a remnant, a time-integrated history captured by the streak line. It wasn't showing the instantaneous flow structure far downstream.
Wow. Okay, that's a really important subtlety. You have to know what kind of line you're looking at.
Definitely. There are other techniques too, like timelines where you mark a line of adjacent particles at one instant, maybe with hydrogen bubbles in water, and watch how that line deforms over time, shows relative motion.
And you mentioned things that don't need tracers.
Right. Refractive techniques like shadowography and Eulerian, they detect changes in the fluid's density by how light bends through it. Great for seeing invisible things like shock waves from a supersonic object, or even just heat rising from a hot surface like a BBQ grill.
Cool. And on surfaces.
We use surface flow visualization, too. Little tufts of yarn taped to a surface or oil flows can show you the direction the fluid is moving right next to the solid boundary.
Okay, so we've got loads of ways to see the flow. But engineers need numbers, right? How do we plot this data in a meaningful way?
Good question. Turning visualizations and measurements into useful plots is crucial. There are a few standard types.
Like what?
The simplest is probably a profile plot. It's basically your standard XY graph. It shows how one property like velocity, magnitude, or temperature or pressure changes along a specific line or direction in the flow.
So like plotting the speed of water across the diameter of a pipe from 0 at the wall to maximum in the center.
Exactly that. Shows the distribution very clearly.
Makes sense. What else?
Then we have vector plots. These are really informative because they show vector quantities like velocity or acceleration. You see a field of arrows.
Where the arrow direction shows the flow direction.
Right. And the length of the arrow shows the magnitude, how fast it's going, for instance. We talked about the accelerating flow in the nozzle. A vector plot would show short arrows going in and long arrows coming out.
And you can see swirls and things too.
Absolutely. Modern vector plots can even be colored, where the color of the arrow represents another variable like pressure. So you get direction, magnitude, and pressure all in one plot. Very rich information.
Okay, those sound useful. And the colorful pictures you often see in CFD results, the ones that look like weather maps sometimes.
You mean contour plots, or sometimes called iso contour plots?
Yes, that's it.
Think of them like topographical maps for elevation. Contour lines connect points of equal value for some scalar property.
Like lines of constant pressure or constant temperature.
Precisely. Or constant speed, even. They immediately show you regions of high values, often colored red in CFD, and low values, often blue. They give you a great feel for the overall landscape of the property across the domain. Colorful fluid dynamics is the nickname sometimes.
Right, okay. These visualizations and plots give us a great handle on seeing and quantifying the motion. Now let's dig a bit deeper. What are the absolute fundamental ways a little chunk of fluid can move or deform?
Yeah, thinking about a tiny fluid element, it can undergo basically 4 fundamental types of motion or deformation.
Yeah.
And usually several happen at once. We talk about them in terms of rates.
Rates, okay. What's the first?
The simplest is the rate of translation. This is just the fluid element's velocity vector. How fast and in what direction is the whole element moving from point A to point B?
Just moving along. Got it.
Second is the rate of rotation, or angular velocity. This describes how fast the fluid element is spinning or rotating about its own center, like a little spinning top.
Okay, translation and rotation. What else?
Third is the linear strain rate. This measures how quickly the fluid element is stretching or shrinking along a particular axis. Imagine pulling on a piece of putty, it gets longer and thinner. That's linear strain.
Stretching or squashing?
Right. And related to this is a really key concept, the volumetric strain rate. This is simply the sum of the linear strain rates in 3 perpendicular directions, x, y, and z.
Why is that sum important?
Because for an incompressible flow, which includes most liquids and gases at low speeds, the volume of a fluid element cannot change. Density is constant. So the volumetric strain rate must be 0.
Ah, so if it stretches in one direction.
It has to shrink in one or both of the other directions to keep its total volume the same. A 0 volumetric strain rate is the mathematical definition of incompressible flow at the kinematic level.
That's neat, a direct check. Okay, translation, rotation, linear strain. What's the fourth?
The fourth is the shear strain rate. This describes how the fluid element changes its shape due to angles changing, without necessarily changing its volume. Think of that square element again. If it deforms into a parallelogram, the angles are no longer 90 degrees. That angular deformation rate is related to the shear strain rate.
So it's about the shape changing, the angles distorting?
Exactly. It's how layers of fluid slide past each other.
Okay, let's tie this back. Remember that steady flow example, the one where the particle accelerated in the nozzle, or that similar mathematical field? What do these 4 rates tell us about that specific flow?
Great question. If we analyze that flow field using these kinematic rates, we find some interesting things. Obviously, there's translation, like the fluid is moving.
Right.
But surprisingly, perhaps, the rate of rotation turns out to be 0. The fluid particles are moving and deforming, but they are not spinning on their own axis.
No spinning, even as they speed up.
Correct. We also find non-zero linear strain rates. It stretches in one direction, the flow direction, and compresses in the perpendicular direction.
Okay, stretching and squashing.
But here's another interesting bit. The shear strain rate is also 0 for that particular example flow.
What does that mean physically?
It means that if you imagine an initially square fluid parcel, as it moves through this flow and deforms, it always remains a rectangle. Its corners stay at 90 degrees, even as its side lengths change. It stretches and squashes, but doesn't skew.
Wow, okay, so stretches into a rectangle, keeps its volume constant.
Exactly. And if you calculate the volumetric strain rate, summing the linear strain rates, you find it's identically 0, confirming that this flow is indeed incompressible.
That's a really concrete picture now. Deforming, accelerating, but not rotating, not shearing, and keeping its volume. This brings us right to that big idea you mentioned earlier, the difference between just revolving in a circle and actually rotating or spinning.
Yes. This is such a key concept and often a source of confusion.
It feels totally counterintuitive that something can move in a circle but not be rotating. How do we define rotation properly for a fluid?
We use a mathematical tool called the vorticity vector. It's calculated from the velocity field using an operation called the curl. Don't worry too much about the math, but the important thing is what it represents.
Okay, what does vorticity tell us?
Vorticity is precisely twice the angular velocity, the rate of rotation, of a fluid particle.
Ah, so vorticity is basically a measure of the local spinning motion.
Exactly. If the vorticity vector is non-zero at a point, it means a fluid particle placed there would be rotating, and we call the flow rotational. If the vorticity is 0, or negligibly small, the fluid particles are not rotating, even if they're moving along curved paths, and we call the flow irrotational.
Rotational versus irrotational. Where do we find these different types of flow?
Rotational flows are typically found where viscosity has had a significant effect. So in the wakes behind objects, in boundary layers right next to surfaces, and inside things like pumps and turbines.
That sees us with friction and shearing.
Pretty much. Irrotational flows, on the other hand, are often found in the outer regions of a flow, away from boundaries and wakes. The great thing about irrotational flows is that they are mathematically much simpler to analyze. And thankfully, many real-world flows, or at least large parts of them, can be approximated as irrotational.
So it's a useful simplification.
Very useful. An interesting property is that if a flow starts out irrotational, it tends to stay irrotational unless viscosity or maybe strong temperature gradients introduce rotation.
Can we see vorticity in visualizations?
Oh, yes. Remember the flow around a block. If we plot contours of vorticity, we see really high values, meaning strong rotation in those shear layers peeling off the corners where the flow separates. It clearly shows where the fluid is spinning up.
Okay, that makes sense. Now back to the big one. Moving in a circle but being irrotational. How?
Okay, the classic comparison. Let's imagine two scenarios involving circular motion. Scenario A, solid body rotation.
Like a spinning record player or a merry-go-round.
Perfect.
Yeah.
Merry-go-round, everyone on the ride is revolving around the center, right?
Right.
But notice, they're also rotating themselves. If you face the center at the start, you're still facing the center halfway around. You've rotated 180 degrees relative to your initial orientation. Your body has spun. This flow has non-zero vorticity. It is rotational.
Okay, I'm with you. Revolving and rotating.
Now, scenario B, a line vortex model. Think of a Ferris wheel.
Okay, big wheel gondolas.
The gondolas revolve in a big circle around the central axle. But how are the gondolas usually designed?
They stay upright, they don't tumble around.
Exactly. They're designed not to rotate. A person sitting in the gondola is always facing roughly the same direction, maybe slightly tangential. But their orientation relative to the ground isn't constantly spinning like on the merry-go-round.
Yeah.
This type of flow, remarkably, has zero vorticity everywhere except right at the mathematical center point. It is irrotational.
Whoa. Okay. The Ferris wheel versus the merry-go-round. That really clarifies it. Revolving without rotating. That's the irrotational vortex. That's the essence of it. And this isn't just theoretical. It's incredibly useful for modeling things like flow into a drain or a sink, often approximated as an irrotational sink flow, even though the streamlines curve inwards.
Mind blown. Okay, that's a huge takeaway. Now, we started way back by talking about Lagrangian falling particles versus Eulerian fixed regions. And we have these fundamental laws like conservation of mass, momentum, energy. How do we apply those laws, which are often naturally thought about for a fixed chunk of matter, to our more practical Eulerian control volumes where stuff flows in and out?
This is the final piece of the puzzle for setting up practical fluid analysis. We need a bridge, and that bridge is the Reynolds Transport Theorem, or RTT.
Reynolds Transport Theorem. Sounds important.
It is the fundamental theorem for relating the Lagrangian and Eulerian viewpoints when it comes to conserved quantities. Most basic laws, mass conservation, Newton's second law for momentum, the first law of thermodynamics for energy, are originally stated for a system a fixed amount of matter.
Like our single particle, just scaled up to a defined chunk.
Exactly. But in fluids, we usually want to work with a control volume, that fixed region in space. Mass flows in, mass flows out. How does the change within the system relate to what's happening in and across the boundaries of the control volume?
That's the question RTT answers.
That is precisely the question RTT answers. It provides the mathematical link.
Can you give an analogy?
Sure. Think about a can of spray paint. The paint inside the can is your control volume. When you spray it, mass, paint, leaves the control volume.
Okay.
Now think about the paint that has been sprayed out, that cloud of paint particles moving through the air. That cloud is a system. Its mass is constant, it's the same paint, but its volume is expanding, its position is changing.
Right. The system moves and deforms. The control volume stays put but loses mass.
RTT connects those two pictures. It tells you how the rate of change of some property for the moving, deforming system relates to the changes happening inside the fixed control volume and the flow of that property across the control volume surface.
So what's the core idea? What does the theorem actually say in words?
It basically says this. The rate of change of some extensive property, like mass, momentum, energy, belonging to the system, is equal to two things added together. First, the rate of change of that property stored inside the control volume. Second, the net flux of that property flowing out across the control volume's boundary.
Change within the system. Change stored inside the volume plus net flow out of the volume.
That's the essence of it. There's a detail about relative velocities, too. If the control volume itself is moving, You need to consider the fluid velocity relative to the moving boundary when calculating the flux.
Ah, like water hitting a moving car.
Exactly. It's the relative speed that matters for momentum transfer across the boundary.
So let me see if I can connect this back. The material derivative helped us link the Lagrangian view, following a particle, to the Eulerian view, fixed point, for rates of change at a point. Does RTT do something similar, but for whole volumes?
That is an excellent way to put it, yes.
Yeah.
You can think of the RTT as the integral counterpart of the material derivative.
Integral counterpart.
Okay. Both of them bridge the Lagrangian and Eulerian perspectives. Both of them essentially break down the total change experienced by the fluid into two parts. A local or unsteady part, changes happening at a fixed location or within a fixed volume over time, and an advective or convective part, changes happening because fluid is moving from one place to another, carrying properties with it across boundaries.
That's a really helpful connection. They're solving the same fundamental problem at different scales.
Precisely. And why should you care about RTT?
Oh.
Because it is the fundamental starting point for deriving almost all the practical conservation equations we use in fluid mechanics and thermal sciences. The integral forms of conservation of mass, momentum, and energy all come directly from applying RTT. It lets us analyze everything from pipe flow to jet engines to weather patterns.
Wow. Okay, what a journey through just the kinematics, the how of fluid motion, without even touching the forces yet.
It's foundational stuff.
We really unpacked a lot, from understanding the Lagrangian versus Eulerian ways of looking at flow,
To realizing how the material derivative explains that seemingly paradoxical acceleration in steady flows. That nozzle example really drives it home.
yeah, and learning to see the flow with streamlines, path lines, and streak lines, and crucially, knowing they're only identical in steady flow. That vortex street example was eye-opening about visualization.
Absolutely. Then we dissected the basic moves, translation, rotation, linear strain, shear strain, and landed on that zero volumetric strain rate being key for incompressible flow.
And for me, the biggest aha moment was definitely the vorticity, and how you can have circular motion without rotation. The Ferris wheel versus the merry-go-round, I won't forget that one.
It's a classic for a reason. It really challenges your intuition.
Finally, tying it all together with the Reynolds transport theorem, seeing how it bridges the system and control volume views, acting as that integral partner to the material derivative. It really provides the toolbox for applying conservation laws.
Exactly. It sets the stage for analyzing almost any fluid flow problem.
So next time you're out and about, maybe you see smoke rising from a chimney or leaves swirling in a puddle, or just watch the air moving around your hand as you walk.
Maybe pause and think. Are those fluid particles really rotating? Are they stretching? Are they shearing? What story is their hidden kinematic dance telling?
This basic understanding of kinematics really is the first step to unlocking the secrets behind almost everything that flows.
It opens up a whole new way of seeing the world.
Well, thank you for joining us on this deep dive into fluid kinematics. We hope you're leaving feeling a bit more well-informed, maybe a lot more curious, and ready to see the invisible currents all around you.